All right, everyone, so welcome back for this coffee talk. Just a quick reminder for everybody to use the hashtag HPE Coffee Talk when you're talking about these sessions, so we actually see each other's messages. The HPE Discover tag gets lost in all of the noise. So this session is Mike Woodacre, who has joined HPE through the SGI acquisition a year ago, and I think quite a few of us have an affection for the SGI as a company from years of history of some very interesting boxes. And Mike is going to be talking to us about the Superdome Flex. So I'll hand it over to Mike.
Great, thanks. It's great to be here. And I think what I was going to do was just give a brief introduction to the Superdome Flex. I expect some of you have some knowledge, but maybe some others don't. So I'll start just by going through a few slides, and then obviously look forward to the questions. So as was mentioned, I joined HP just over a year ago, coming in from the SGI acquisition. I've been working at SGI on large memory platforms actually for the last 20 years. Back, for those of you with long memories, to Origin 2000 back in the mid-90s, back when we were building our own MIPS processors, our own IRIX Unix operating system at SGI back then, building our own memory DIMMs, our own cables, our own I/O channels. And then we've kind of come through this evolution of adopting more and more open industry standard components but distilling down the core value we bring in how we build these scalable in-memory computing platforms. And so just over a year ago, we got together with the HPE Superdome team and basically immediately got the engineering teams working very closely together on what was announced 2 weeks ago as the Superdome Flex platform. And it truly is I think a really good representation of all that's been good about the acquisition of SGI by HPE. It's been a very fast-paced first year, but we've now launched this first major platform to come out of the acquisition, and it's already getting some great attraction from customers. There's going to be one of our key customers on stage in the main presentation this afternoon. I can't disclose that now, unfortunately, but that should be a lot of fun. So Superdome Flex, really, what is it? It's a modular, scalable in-memory platform, and as you know, the previous generation was Superdome X. That was HPE's first move into x86-based large shared memory machines. And the Flex name really is key to what this product is about. It's bringing a finer grain modularity to deploying these systems, and I'll talk more about that. The fact that you can start small. You can start with a 4-socket chassis, and then when you want to grow that system, you just buy another chassis, you cable them together using our memory semantic fabric reboot, and you've got a bigger system. And you can grow that from 4 sockets all the way up to 32 sockets in a single rack, and up to 48 terabytes of memory in that single footprint. That would be using 128 gigabyte DIMMs. So really this easy to consume unit of compute and large memory technology. And obviously in a year we don't go about building a new generation of fabric and the ASIC technology. Obviously that work was already underway at SGI prior to the acquisition. But what's been really key, and I'll move on to the next slide, is this slide is trying to highlight what we've done is bring together the best elements from the Superdome X from HPE with the previous shared memory systems from SGI, the previous generation at SGI being the UV300. Interestingly, HPE were already OEMing that platform and called it the MC990X. And the reason HPE were already OEMing that was really to fill the gap below Superdome X. Superdome X was really optimized for 16 sockets. So the entry, if you just put 4 sockets in that Superdome X, it was a costly entry point. So with the modularity of the UV300 and now the Superdome Flex, makes the entry point much more cost effective. So from the Superdome X, we have the heritage of the firmware development at HPE. So around reliability, HPE obviously has been in high-end enterprise systems for a very long time. So there's a lot of heritage in that firmware stack. There's also a lot of investment in security features and manageability features that enable these systems to be used in mission-critical environments where any downtime literally stops a business operating. So it's very key that if there is any issue with the system, that you react to that in real time and you get as much of the system back online as soon as possible to minimize that downtime. So that's really the mission critical heritage from Superdome family HPE. In addition, we'll be adding NPARS support. This is basically the electrically isolated partition support. Again, this offers a lot of flexibility if you want to deploy different operating systems within a single environment. Gives you that manageability. Also, we've brought, coming from the SGI background, we just supported Linux on our platforms. Again, HPE has been supporting Windows and VMware, as well as Linux on previous Superdomes. We'll be adding that support as well. So you can have a single rack system, you can use the partitioning to either run it as one single machine, or you can divide it up, running different operating system, different environments. Lots of flexibility. The other piece, if you look at the Superdome X, it was using proprietary I/O cards. So it was leveraging from the previous Superdome platform to obviously accelerate that platform's introduction. But with the pace of development now in I/O-based accelerators, it's really important to, again, embrace industry standards. So having the support for standard PCIe cards gives us lots of flexibility. Classic example right now, people, there's obviously a lot of interest in machine learning, artificial intelligence, and GPUs are obviously heavily used in machine learning training. We can support GPUs in this platform. We can support FPGAs. We can support high bandwidth networking cards, so InfiniBand, OmniPath, high-performance Ethernet. We can support high-performance NVMe flash storage in the platform. So again, this provides a lot of flexibility. So if I move on to this next picture, in terms of the processing, we've introduced the system with the latest Intel Xeon scalable processors. Skylake, right, is the key thing. And what Skylake does is a key feature of Skylake is the big boost in memory bandwidth it's bringing with the additional memory channels. So we're seeing about a 50% boost in memory bandwidth compared to previous generation. It also has the memory directly attached to the processor, no memory buffers that we had in the previous generation, so that reduces local memory latency. Another key change, and this is a little more subtle, is Intel moved from the QPI, the Quick Path Interconnect, to the UPI, Ultra Path Interconnect with this generation. And for most people, that's a really low-level detail, but when you're building these scalable shared memory systems, it's a real key difference, because the sort of real low-level detail difference is with QPI, when you booted the system, you had to divide the number of outstanding memory references between how many processing elements were accessing that memory. And that was sort of a hard limit, hard allocation at boot time. With the UPI, there's no hard allocation. So what this means is I can send all my memory references to my local sockets memory subsystem to drive that at very high performance, or I can point all of those memory references at my fabric that's connecting these chassis together. So obviously when you go between chassis, there's additional latency than if you're just talking to your local memory. But by having UPI letting me send all of these memory references over that fabric, I can help to tolerate that latency more effectively. So UPI is a big step forward in making this, improving the overall system performance. So then the secret sauce in how we connect these chassis together is the node controller fabric that we've got basically sitting under the motherboard. In this picture, you can see the interconnect board that has two of our node controllers. And then we use industry standard 100 gigabit QSFP connectors coming out the front of the chassis that we then cable these chassis together. And I have a picture coming up on the topology that shows how they're all connected. But the key, again, is use industry standard components so we can reduce cost. We're actually using OmniPath 100 gigabit cables today because they're the most cost effective in the industry today. So then, looking more in detail at the topology, when we put these units together, we can put up to 8 in a single rack, and we have enough connectivity with our memory semantic fabric. We can have a direct connection from every processor to every other processor in that single rack. And why is that a good thing? It means that you've got the same latency profile when going between any chassis in that rack. So for someone like SAP who's tuning HANA to run on a large in-memory database on the system, this means I start out with my 4-socket building block. When I add my next 4-socket building block, I pay a latency penalty to go over our fabric. But then as I add additional modules to the system, I have that same latency profile. So this means that if you talk to a CIO today and then how big's your in-memory database need going to be in 3 years' time, most of them will say, I don't know. I hope my business successfully keeps growing, but how big my requirement's going to be in a few years, I don't know. With this modular architecture, we can basically have this pay-as-you-grow deployment, so you can add modules, but then from an application performance perspective, you're getting the same latency and bandwidth profile as you grow the system. So this really, is a powerful story to sort of future-proof your systems. Equally, people can start, in that sort of enterprise environment. Today, they may be running scale out. You could have that single rack with 8 of these chassis in, and you could run 8 scale out applications today. But then when you're ready to scale up, to switch to in-memory SAP HANA solution, you just reconfigure the system using the partitioning technology to run as one single system. So I already mentioned some of the I/O flexibility. This picture is really just highlighting the fact we can either have a large amount, 16 low-profile PCIe Express cards supported within the single chassis, or optionally we can support 8 full-height PCI Express cards and 4 low-profile. And typically that configuration is actually used when we want to deploy GPUs, which typically come in full-height, double-wide form factor. So we can put 4 300-watt GPUs in this chassis. There's no PCIe switching. We're basically bringing all 192 PCI Express Gen 3 lanes from the 4 CPUs to the rear of the chassis, and then making those available for I/O expansion. So, if people are ingesting, large data feeds into memory, we can basically ingest at very high rates to move move data into memory. A key piece, obviously, in a large shared memory system is you're essentially running one operating system on a large number of components. So you kind of have, I've got all my eggs in one basket kind of scenario. If something bad happens, then potentially, you know, I take a large resource offline. So both SGI and HPE have invested heavily in reliability features over the years. One I will highlight with this latest generation of our interconnect is I showed that all-to-all topology where you have the lowest latency direct connection. We also support adaptive routing in the fabric, so you can actually bounce traffic off other nodes in the system if you're trying to drive more high bandwidth data. We take advantage of that adaptive routing capability, that if a cable did fail, that we can actually pull the packets out from the lowest level transmission and reroute. So you can literally go up to one of these systems, pull a cable, and it will keep running. Marketing won't let me make that video because they're worried if I make that video, everyone's going to start pulling cables. But we put the features in. So that's just an example of a next step we're taking in the reliability. And then I did want to touch, you know, just a little bit on sort of future directions. One of the things coming into HPE a year ago, I was really keen to find out about the machine. You know, the HPE had made public announcements around the machine, you know, about 3 years ago. And, you know, when they first started talking about this memory-driven computing, memory-centric computing, this really intrigued me because our architecture at SGI was you know, very much in line with that thinking. So I was very keen to find out what technologies were going on, both the you know, technologies around high-speed fabrics, optical interconnects, persistent memory. But for me, actually, I was really keen on the software side. We'd actually put a lot of features into our architecture at SGI that we just didn't have the resources to really invest on the software side to take full advantage of. And the good news is we can leverage that work that HPE Labs were doing on memory-driven computing, and we've already ported the software over from the machine prototype testbed to run on the previous generation, the MC990, and we're working on the Superdome Flex port too. So you know, as we look to the future, we obviously see areas where people, you know, in this world of ever increasing data sets, you know, getting that data in memory just can give you orders of magnitude speed ups. And so actually I switch to this slide. This is some research that the labs did on a number of sort of different applications or workflows, showing some of the speed ups that they could get. The interesting thing is these numbers are actually obtained on the Superdome X, so basically making use of the previous generation of the large shared memory platform at HPE. And actually at SGI, one of these is highlighting DZNE, who look at Alzheimer's research, so life science research, where the labs have worked with them to get 100x speed up on their workflow. Actually, SGI had done a lot of our shared memory customers are also life science, where you have these massive data sets. You're working with new algorithms, so it's not like traditional HPC where you've got some computational fluid dynamics code that's been worked on for the last two or three decades, highly tuned. You've got people looking at the latest sequencing data, trying to figure out, you know, genomic anomalies, and they want to rapidly look through the data, try and figure out new properties to look at potential cures for diseases. So there's huge opportunity for speed up. In the financial area, this was a financial risk analysis. So this was basically turning some aspects of Monte Carlo simulation into lookups. So pre-computes partial results put those partial results in memory, and then when you're actually doing the real-time computation, you can do a lookup and then a small iteration from that base result to the final result. So by rethinking in a memory-centric way, you have a lot of opportunity for speed ups. And then this final slide I'll show is really, I mentioned we're porting that machine stack onto the Superdome Flex. Well, we've productized today up to 32 sockets in the single rack. We can actually look in the future to potentially grow that higher. At SGI, we've previously pushed our architecture higher. So we really see the Superdome Flex as the on-ramp, for this memory-driven computing world. Today, we can deliver you a production 48 terabyte single system image machine, and we sort of have a path in the future to moving in, from tens of terabytes to hundreds of terabytes, and ultimately, petabytes of in-memory data. So, it's the most exciting roadmap I've been able to talk to customers about. Obviously, this is a public forum, so I can't go into all the NDA details, but obviously working with partners like Intel. We're also, Intel has publicly talked about where they're going with 3D XPoint, their persistent memory technology. We'll look to integrate that when Intel brings it to market. So there's just a tremendous roadmap ahead for this, directly addressable in-memory data set model that can really bring latency of access to data down into the nanosecond rather than millisecond. Basically have 4 CPUs talking to 2 of our node controllers in the in the fabric, and then each of those ASICs is real. That's the secret sauce. So we're tightly coupling into Intel's UPI interconnect. So we have a direct connection to the processor's coherent memory subsystem. And what our node controller does is it basically acts as a proxy for all of the other processors and memories across the fabric. So when you're inside a chassis, you've got the 4 processors that are directly connected, and then they see our node controllers, and to those processors, our node controllers look like additional processors. And so basically, it's all, if you're running a single Linux kernel, the firmware, when the system boots up, will present all of the cores, all of the memories as one single set of resources, through the ACPI firmware tables. So then when the OS boots, it just sees 32 sockets, hundreds of cores, many terabytes of memory. And, we've worked with the Linux community over many years to scale Linux to support, well, today it supports up to 64 terabytes, 8,000 cores in a single kernel. And actually SGI already has systems deployed in the field with, I think the maximum we have is 4,000 cores, but we do have 64 terabyte systems deployed actively with customers today. So from an application standpoint, you just see this big pool of cores and memory. That's the beauty of the shared memory programming model, is it's the ease of use. Obviously, we can run MPI codes on a shared memory platform, but you also get that ease of use of I can do a processor load store to that entire data set. So this is where you can just start thinking differently. With a cluster, the first thing you've got to do is think about, how do I do a domain decomposition? How do I slice up my data set across all these nodes? And then how do I transfer messages between the nodes? That's okay to do if you've got a very well-constrained problem. It's a very well understood problem, so you know how to distribute that data. And in the internet world, a similar thing too. Google or whatever, they slice up their searches, scale out, works great because it's a very distributed workload. But when you're looking at, let's think about graph analytics. When you're navigating a graph, you don't know where your next vertex in that graph is going to take you. You know, so if you're searching through a graph, if you have this single address space, it's very easy to program in a shared memory world to look at where to go next for data. So one of the things we've done in the past is have customers working on things like fraud detection. You know, when you press buy, you know, on the internet, what typically happens, you know, by people who want to prevent fraud is they'll in a very short period of time do a graph analysis to make sure it's you pressing the buy button. It's not a bot. It's not, you know, it's not a, you know, if they see this credit card's getting used 1 million times in this second, you can guarantee that's not one person buying 1 million things, right? So you have this real-time need to do a graph analysis, looking at large data sets. So having that in-memory data available in near real time, that's where you can transform the way you start analyzing data. And you know, what's key in productivity is, you know, as humans, we're always, what's the next question? What's the next question? And so by having data in memory, you're able to speed up what's the next question in a sort of you know, an easier to manage way than having sort of hard boundaries in a cluster environment.
I don't know. Does this work? Can you hear? Okay. One of the key messages that we keep hearing from HPEs over and again is simplify hybrid IT. Taking the traditional, marrying it in with wherever things are going, cloud, storage farms, whatever. Have you been in, or do you see a role with this when you mentioned like SAP HANA of being part of a hybrid where it's just running SAP HANA and is easily approached by any applications running on traditional systems? Can you sneak into data centers in a way that's part of this hybrid IT?
Yeah, so I mean, there's already the ability to run, you know, SAP HANA in the cloud, and you know, some of those platforms that are underlying are previously SGI and now HPE systems. So I think, so what we're trying to do is obviously make the IT easy to consume. People, you know, want to make it easier to consume IT. So, you know, we're doing that in a number of dimensions. We are looking to increase sort of, you know, large memory system availability in cloud infrastructures, whether it's on-prem or off-prem. We're also able to support, you know, HPE has flex capacity. We're able to offer that with this infrastructure as well. That's you know, seeing a lot of attraction from customers. They like that flexibility. One of the key things, obviously, with the Superdome Flex is because it is modular, it's easy to incrementally add to a resource. So if you are seeing growing demand, you can add modules, grow your system capability. So that sort of underlying architecture can scale and grow. We're providing on and off-prem solutions. We're providing flex capacity. So we're trying to make it as easy as possible to you know, give users access to this technology, because you know, again, if you know, people who've got very large data set needs, you know, we're talking to customers who, you know, literally say, I'm doing all this scale out compute, but I've now got a 50 terabyte data set I need to do kind of analysis on, and I don't know how to do that. And the sort of analysis work I need to do needs to be in one memory. So again, they can use this technology to solve that problem. But it's not to take away I mean, clearly the scale out piece, when you've got compute intense pieces you need to do, scale out is a perfectly good way to go. We've got lots of platforms for that. But some of the analytics, you just want to be able to follow the data, see where it leads you.
I think you talked a little bit about resiliency features that you were architecting into the Superdome Flex. In a grid-based architecture like this, we know operating systems don't like to lose memory or PCI. Can you talk a little bit more about how you protect against that, and what are the impacts when you do have a chassis go down or that sort of thing?
Sure. So let's start with how RAS, reliability, availability, serviceability. It's kind of this continuous process improvement thing. It's like you can never do enough. You always want to be doing more. So we're always looking at how to improve that capability. I mentioned the ability to tolerate a cable failure is something we added. In terms of memory, we've worked very closely with, obviously, the memories are hanging off the Intel processors. So we've worked very closely with Intel to basically improve the reliability of the memory error processing algorithms that are going on. If you look at the information on the Skylake processor, you'll see it has advanced double device data correction capabilities, so you can have multiple DRAM failures and the system keeps running. So HPE obviously pays a lot of attention to that particular area. Ultimately, if a CPU dies, the system's going to crash. I mean, or if you get a catastrophic memory failure that's recoverable in kernel space, you're going to panic and crash. I mean, if you get unrecoverable memory errors in user space, there's support in the platform, so we can just kill the process, the user level process that was running, so you don't have to take the whole system down. And we can also inform the operating system if we see areas of DRAM is starting to have multiple correctable errors. We can actually basically inform the operating system to migrate data away from an area we think may turn bad. So you can kind of do these preventative things. So we do that. Ultimately, if you do get a catastrophic failure, the system's going to panic, it's going to crash. But then with the management firmware we have in the platform, we have what's called the error analysis engine running in our management controller. And so this is looking at it's basically got touch points into all the components to look at what's going on, and then it can deconfigure components. It can deconfigure CPUs, it can deconfigure memory, it can deconfigure I/O, and then bring the rest of the platform back up and running. So we also support high availability options. So for instance, in SAP HANA, when people are in production, they'll typically have a hot standby. So if you do, you can fail over to a standby system and keep running. And then typically you also have a disaster recovery system, off-site, which you could ultimately fail over to as well. So there's multiple layers to how do you deal with the reliability. So ultimately, your building systems, high performance components will ultimately fail, and so you need to make sure you've got a strategy that can deal with that. And so that's why ultimately we do have the high availability option. When uptime is absolutely critical to a business need.
How have your customers changed over the last 5 or 10 years? And how do you see them changing going forward over the next 5? I mean, this is a lot of change both for your product line and in terms of technology. So kind of what's the big shift for the past few years and where's it going?
So I come from SGI, more from a high performance computing background than the mission critical business computing. But I'll talk a little bit about the HPC side, and then how that's then translated into the enterprise mission critical side. So, SGI, we were building large memory systems for 20 years or more now, and the key was really scientists who would use the platforms were looking at how can I really gain insight to my problem in the most productive way. And obviously we've seen the rise of clusters in HPC over the last more than a decade, where obviously price performance has been a key factor, and also scale. You can scale clusters to tens of thousands of nodes to 100,000 nodes. The scalability is really of high performance applications has really been driven by clusters. But even within the HPC application area, where we sell a large scale out cluster, people would buy a large shared memory machine for a few areas of use. Typically pre-processing, post-processing, visualization, and also proof of concept work. So for pre-processing, before you run large structural simulations, you're creating meshes. Again, this is something that a single address space can really help you with. Post-processing, when you're doing analysis of the simulation data, again, you want to look at the whole data. You don't want to filter data. You may also want to do in-memory visualization. That's where the large memory systems have been useful. Also, when you're prototyping applications, even MPI applications, when you're trying to add more science to your models, it's really helpful. It's really productive in the shared memory environment where you're not going to have a node run out of memory because it can grab memory from elsewhere in the system. If you're running on a cluster, once a cluster node tries to allocate memory that's not there, bad things typically happen. So a lot of our MPI, our customers who focus on MPI applications will actually develop those applications on the shared memory platform because it's an easier sandbox to do development in. Then what we saw at SGI and HP was the same. SAP wanted to transform how business transactions and analytics works together. The move to in-memory database, and ultimately that SGI saw that opportunity, started selling our systems into the SAP HANA world, and that's ultimately what drove the acquisition by HPE, seeing the same growth, same architectural alignment. So what you started to see is businesses wanted that higher speed analysis of data. So you're not looking at with a data warehouse at what your business did last week or last month, but you're seeing what it did right now. So by combining the transactions and the analytics into your hot data that's sitting in memory, you can basically see what your business is doing right now and take make real-time decisions on how your business is operating now. So that and some of our leading customers now have tens of terabytes of data. They want to be in that world where tens of terabytes of data are sitting in memory for that real-time capability. So both companies saw that as an opportunity to build platforms that can deal with those challenges. And then as we look to the future, we see that those challenges are just continue to grow. The amount of data people are wanting to use to influence decisions is just growing, whether it's sensor data, whether it's social media data, whether it's instrument data. So actually we see some of the needs of HPC and some of the needs of high performance business kind of converging. People with these faster growing data sets, it's no longer possible for people to write the algorithms to analyze that data, and so that's why we're moving into this whole world of machine learning, artificial intelligence. because people, in the old days with a CFD code, you understood the Navier-Stokes equations, you wrote your MPI code, but now you're looking at all this data and that's coming in from various sources, and we can leverage the scalability of compute to basically create the equations, the understanding of what's going on in that data. And we see this both in science and in business, the need to analyze those data streams, and whether it's making scientific understanding or business understanding of that data, these needs are just driving forward in both areas. So where does this end? Who knows? But I think clearly, from some of the speed ups I showed you, that having data sets in memory allows you to achieve. I think this is a new dimension of optimization people can make for real-time analysis to get more value from their data. So I think it's another tool we have to gain insight, gain value from data.
Mike, I wanted to just dig back into the hardware piece and understand that the node controller is really tightly coupled to the CPU architecture, and that there's a redevelopment of that node controller every time Intel changes out their processors. Can you talk us through how that partnership with Intel and that respinning of the ASIC sort of affects the life cycle of the product?
Sure, yeah, no. So we've been, both HPE and SGI have been working closely with Intel building these sorts of systems for more than a decade. So we've got really tight coupling with the teams. Obviously I mentioned the transition from QPI to UPI. That was a change in protocol, so that required a new ASIC. So obviously, in some ways that's a painful transition, but it's also a necessary transition in the sense that you have to keep the system in balance. So as Intel is working on improving the core performance, number of cores, their memory subsystem on the socket, memory bandwidth, memory latency, if we're putting lots of these processes together, we need to keep that system in balance. So we need to keep trying to squeeze the latency out of our interconnect, drive to higher bandwidths on that interconnect. And, and that certainly with the Superdome Flex, we've been able to essentially, if I compare against the previous generation MC990, Intel improved the local memory latency by taking the memory buffers out by 25%. Memory bandwidth was a 50% improvement. We have a similar 25% remote latency improvement with our ASIC and about 50% bandwidth improvement. So we've kept the overall system in balance. Because if we don't keep up with the processor, then you're just why bother having a really high spec processor if you're just waiting for the fabric? So you've got to keep driving forward. What Intel typically does is have more than one processor within a family that can talk to the same protocol. So, for instance, we're expecting more than one processor to talk what we call UPI 1.0 before Intel moves on to a UPI XXX. But we work closely, and so it's a question of deciding when's the right point to work with Intel, where we think they're making a big push forward in the core processor capabilities, and so we'll similarly look to move the interconnect forward.
And then as you're seeing this architecture deployed out into customers, are you seeing the single large-scale rack system actually being carved down into the separate end-paths, or are you seeing them primarily being used as a single large machine and running a single large workload?
So we're seeing both, essentially. I mean, initially, there's always a few sort of flagship customers who want to go large straight away. So, one of those will be announced later today. And then the NPARs we're introducing in the first half of next calendar year. That's not released in this early access program. And typically the customers who are looking at more fine grain, sort of, partitioning of the system, they're generally not needing to push forward as quickly as the ones who have the high-end requirement, who want the biggest thing as soon as possible. So they're fine with that sort of later deployment of the partitioning capability. So but we're definitely seeing demand by, I've been talking to customers here on the floor, and I've had both ends of the spectrum. People, how can I partition down? How can I start with scale out and then convert to scale up, as well as I want to go to more than one rack. So it's, yeah.
And what are the use cases that are driving that use of hypervisors on top of this single large system? We normally associate hypervisors with a scale-out cluster architecture rather than a very big scale-up.
It's really flexibility. People, just they have legacy workloads. They want to keep running legacy software environments to keep alive. Typically, it's the high-end platform is when it's a single use case that kind of drives that more. The hypervisors are more, for just flexibility, really. It's and the legacy support of applications. No one wants to stop running things. They want to keep running what they've been running forever, and then add on. So that's really where the hypervisors give you that flexibility.
It's that scary accretion of IT that we need more mass extinction events to get rid of old IT.
Yeah, no,
Careful, Alistair.
Oh no, I'm thinking Y2K was a mass extinction event of IT, and our next one is the Unix date format change. That's going to be another mass extinction, but that's a long way away.
I've got a quick question for you. We had a chat. Your boss is Randy Meyer. Randy was instrumental in driving this deal. Randy's heritage is really entrenched in product management in tandem and nonstop. And I was curious about you not being allowed to pull cables and things in case the customers rush off and doing this. But have you talked to Randy about that? Because his intro into the whole company was he was pulling disk drives and CPUs and processors, and I think he warmed to doing that on film.
Yeah. So nonstop is a key piece of the business unit. Actually, prior to SGI, I used to work at MIPS with MIPS and Tandem. We're using MIPS processors in lockstep mode. So my first trip to Austin was when Tandem called up and said, "We got these two chips and they're falling out of sync by one cycle. Can you come and tell us why?" So I spent a week in the lab in Austin trying to figure out why these two chips were going out of sync. So yeah, that mission critical nonstop environment is a very important business. We're obviously looking to just continually move technology forward, but it does get as you push performance that everyone wants to do, you do run up against reliability challenges because you don't have these nice connection points that you used to have because you want to run signals faster and signals don't like transitions. So it's there's a tension there between how do you drive performance versus resiliency, reliability, and I think we are doing investigations into just like today, nonstop is actually a software. It's no hardware. It's now a software-based product. I think we'll add higher levels of software based resilience to to provide more insulation from hardware component failures, because again, everyone's going to want the fastest memories, the fastest cores, fastest interconnects, and so we're going to keep pushing that dimension. So inevitably, we'll need to provide more kind of software insulation for when components will always fail at some point. It's inevitable, right? Yeah. So you've just got to be, again, have the right layers in place to deal with that. So.
Well, I think we've exhausted the questions here. So thank you very much, Mike. That was really informative.
Great. Well, thanks for the time and the questions.
And we will be taking a break from the stream for a while. It's lunchtime here, and we'll be following that with a keynote. We'll return talking more memory-based compute in 4 hours' time from now, where the HPE Labs team will be joining us.